first one was geometric. What about our next one? P series, okay. Cool. What about our next one? Thoughts on that one? Okay, we can come back. What about my next one? So I'm looking at the bottom left. Does it look close to anything? Maybe even something that we have up there? It looks close to a P series. Is it quite a P series though? No, okay. But it is like P series-ish. Yeah. P series-ish. We okay with that? Okay. What about my next one? What would that one might be a good candidate for? Yeah, right? Because we could just use a basic use up. Yes? Okay, what about my next one? Well, does it look similar to something that we also have up there? Yeah, it looks similar to this one, right? But we have some extra in stuff up here, yeah? Okay, well, so it means like if it was a little bit simpler, we would be able to use our integral. Yes? So we'll say that this is integral-ish. Yes? Are we okay with that? Okay, so now maybe if we've detected a pattern, what do we think maybe, what does this one look similar to? Or geometric, right? We just added, or attempted to multiply, but we put an n on top, right? So still geometric, but not quite, so geometric-ish. Yes, no, maybe. Are we all okay with that? So we're looking at ones now that like we can't quite use one of our nice pretty ones like geometric, P series, or integral, but we're looking at ones that are maybe close to it, okay? Are we with me there? So I can't directly use my P series or my geometric series or our integral test. However, what we can do is compare it to one of the series and talk about it that way. So our first is our direct comparison test. Okay, I'm going to draw you a picture because I think the picture helps. Okay. So A sub n, I'm also going to write this out. So A sub n is our original. Okay, B sub n is our okay, so think about what does it mean for something to be convergent? What's happening graphically? It approaches 0? What was it? Does it have to approach 0? Right, so I'm talking about my sum, right? So it doesn't necessarily, it can approach 0, right? But it just has to approach something. So like at some point, right, we are curving off to where it approaches something. Yes, we don't know what that something is, but it just is approaching something for our sum. Are we okay with that? Yes, no, maybe. So I'm going to say that this is my B sub n. Okay, That's what I'm comparing it to. Because I have information about B sub n. It's what I want to compare it to because B sub n is a nice pretty one that I know it converges. But notice that my inequality here, right? We know that for all things that A sub n has to be less than B sub n. Yes? So even if I don't necessarily know a whole lot about A sub n, if I know that it has to be less than this, so it could be down here, right? Yes, no, maybe? It's going to have to stay below that. Agreed? So we know that it can't shoot off. Yes? We also know that it's greater than 0, correct? Which is why it can't shoot down. Are we okay with that?
Yes.
So if it can't shoot down, which means it can't go towards negative infinity, and it has to be below something that we know is convergent, what has to happen with that thing too? It has to converge to something. We don't necessarily know what it converges to, right? Because remember, most of our tests don't tell us what it actually converges to. It just tells us that it is convergent. Are we okay with that? Yes, no, maybe.
Yes.
Okay. Now, on our second one, this time our A sub n is our comparison, and our B sub n is our original. So this time, so I'll use my green again, okay? So we know that, again, they have to be bigger than 0, so it can't shoot down. But we know that A sub n diverges. Yes? So what does that mean is happening? If it can't shoot down, but we know it diverges, what does it have to do? It has to shoot up, yes? It has to do that somewhere. And that's my A sub n. Yes, no, maybe? And this time we know that B sub n is, we kind of have to think about it the opposite direction, right? B sub n is a what to A sub n? It's greater than, right? Which means that at some point, can it start to go towards a certain number if it is always bigger than A sub n? No. So it would also have to diverge, right? Because if this one's shooting up and I know that my other one is always bigger than it, then it also has to go up as well.
So this is kind of like the squeeze theorem where...
Right. Yeah, it's like your squeeze theorem for like limits, except instead of having 2 things that it has to be between, it's only like 1 thing that you have to compare to. Because we're talking about convergence, like we already are bounded by either convergence or divergence, so that kind of acts as our other thing, right, that we're comparing it to, so we only have to compare it to 1 function.
How do we make sure that one is always greater?
We'll look at that. And that just comes from picking your compare. So like we're going to be given an original function, right? Then we get to pick what we want to compare it to, right? So we're just going to have to strategically pick something that is either always bigger or always smaller. Yes, no, maybe? Are we okay with that? And we'll look at how we do that. So verbally speaking, if you think a series converges, right, we need to compare it to a converging series, but that series that we compare it to should be larger, okay? If we think a series diverges, we want to compare it to a diverging series, but the series that you compare it to needs to be smaller. Are we with me there? So it says determine which of the following series converges or diverges. So first things, let's think, that's a cubed root, by the way. The cubed root of n on the bottom. We kind of need to decide, okay, do we think, because that's our starting spot, do we think this thing converges or do we think this thing diverges? Okay, which is also helpful then, kind of like that first page that I had, to start to think like, what does this look similar to? Okay. What does that look similar to? Yeah, it looks similar to a p-series, okay? So if I'm thinking about a p-series, if I have an n to the 1/3, right, on bottom, what would that do? By our p-series.
Diverge.
It would diverge, right? Because p is less than 1 and in between 0. Alright, I'll write that. Yeah? So like our assumption, we have to prove it, but our assumption is that this is probably also going to diverge since it looks close to that. Yes? Okay. So then we just have to decide, okay? So the thing that I'm wanting to compare it to would just be 1 over my cubed root of n. Yes? And remember, if it's diverges, okay, right, shooting up, I need my original function to be bigger than the function that I'm comparing it to. Agreed? Now, would we agree that me multiplying by 7 for all of my terms, it means that it's going to be bigger than it on all of our spots? Right, so we can confidently say that 7 divided by 3/3 of n has to be greater than that. And so if my 1 over the cubed root of n has to diverge, my original is then bigger than that for all of my n, right? It will also have to diverge. So we are going to say for greater than 1. So then we can say since the sum of 1 over the cubed root of n diverges, since, so we said that we used our what? For that one? P-series, right? So it diverges because our 1/3 is smaller than 1. By B. Direct comparison test. The sum of 7 divided by the cubed root of n diverge. What questions do we have on that first one? Yeah.
For an AP test, if this was like a 3-response question, would we have to have n equals 1 to infinity on both sums? Or do you think they would still take it?
I think they would still take it with the sum, because again, you're trying to write out, because you could also put the sum of a sub n, right? Like, and that would still work, so.
So as long as we acknowledge that it's like for all
The
n greater than 1.
Yeah, and that you're acknowledging that it's not necessarily a sub n, it's the sum of a sub n, then you're okay. Alright. Other questions? Okay, now looking at part B. What do we think about that one? What does that look close to?
Geometric.
Okay. What geometric is it close to?
What do you mean, what geometric?
Yeah, like what would be the thing, the geometric sequence that it's close to? Or looks like? So what does a geometric series look like?
Base to n?
A base to an n. Okay. Do I have things that are to the n power on there? Okay, which things are to the n power?
2 and 3.
The 2 and the 3. Okay. Do we agree that like if I were just like to drop my 1 there, right? And I just had 2 to the n divided by 3 to the n, I can also write that as 2/3 to the end?
Yes.
Yes, no, maybe? Are we all okay with that? And that 2/3 to the end is a geometric series. Yes? Is that a convergent or a divergent geometric series?
Conversion.
It's convergent, right? Because our R is smaller than 1. Agreed? Are we all okay with that? So if we're going to say that this is convergent, yes, goes to something, then what do I need my original function to be then? Smaller, right? My original function has to be smaller than that in order to also be convergent. I think that drawing like a quick picture is helpful, right? It doesn't have to be super accurate, but just saying, okay, is this going to something or is it shooting off? So then do I need my thing to be bigger or smaller than that? We need it to be smaller, okay? So what did I have to do in order to get from my first to my second function?
Make the denominator larger.
Yeah, so like I added a 1, agreed, in my denominator. Yes, no, maybe? Okay, so if I add a 1 in my denominator to all of the numbers that I'm going to list out, what's that going to do to the overall fraction?
Make it slightly smaller.
Make it slightly smaller, right? As I make my denominator bigger, it makes the whole fraction smaller. Do we agree with that? Yes. So we can confidently say that 2 to the n divided by 1 plus 3 to the n has to be less than that. Now, the more you do these, the better that you get at picking what you want to compare it to. Okay. But then our conclusion statement is just then since. Sorry, I need to write. For all n greater than 1. Okay. So since we know that our sum of our 2 to the 3rd to the n converges because our 2/3 is less than 1, right? And it's a geometric, then what can we say?
By the direct comparison test, the sum of 2 to the n over 1 plus 3 to the n converges.
We're all very quiet. Are we soaking in or are we confused? Soaking in. Okay. Do we have questions on either how we picked the things that we were comparing it to, or how we know it's greater than or less than? There is a reason why we do this one later, right? Your limit and your direct comparison are two of your more not necessarily complicated, but they do require a little bit more thinking than your other ones do. So it's okay to be in a little bit of okay, this makes sense, but you're just not quite clicking on all of the things yet.
So whenever you're picking your comparison, you pick it based off a simple version of the function
Yes.
that you know is bigger or smaller than yours.
Correct. Now, we will look at an example, right? Let's say that this is just kind of generally, let's say my plus 1 was up here instead, right? And so I still picked 2/3 to the n, yeah, right? Well now, if the plus 1 was on top, now my original function is bigger than my comparison function, and since my comparison function converges, I can't use that one. Does that make sense? So if you start picking something and you can't confidently say it's either bigger or smaller correctly, then either 1, you picked the wrong thing to compare it to, or 2, we can't use our comparison test. Does that kind of make sense? Okay. Is that where we're getting like hung up on? Is like how we're choosing what to compare it to? Because it does seem like a little math magic as far as like we're just picking something, right? There's not like a formula that's like this is what you do every single time. I get that. Okay, let's look at our next one. What do we want to do here? This one is going to be even a little bit more like, let's think through things. So like, what did I end up doing for both A and B? Like to figure out what I wanted to compare them to. What did we get rid of? A number, right? Just a constant, right? We ended up getting rid of constants. Okay. Do I have constants here? Yeah, okay. So if I just dropped those, alright? Again, thinking like, okay, well, the patterns worked so far, let's continue with the same pattern. If I just drop my -1 and my 3, what would I end up with? Yeah, I get n over n cubed, which is just 1 over n squared. Alright, okay with that. Now, would 1 over n squared converge or diverge? It's going to converge by our p series test, right? Because p is bigger than 1. Alright, okay with that. Okay, so that means that, again, drawing my nice green picture. If the one that I'm comparing it to converges, what do I need my original to be? Less than. So I need my original to be smaller than that. Yes? Okay. We need to convince ourselves of that. Okay, so this is where sometimes it's helpful just to plug and chug a little bit. We can think through it critically, right? If I'm making my top smaller and my bottom bigger, right? Either one of those in and of itself would make the whole thing smaller, right? Subtracting from the top or just adding to the bottom gives me a smaller fraction. So doing them together is just going to make it even smaller. Agreed? But if it's helpful, right? If we need to convince ourselves, because if you're not convinced that that thing is smaller or bigger appropriately, then your reader might not be convinced either. Are we all okay with that? So we could just plug in some numbers. What do we get if we plug in 1? To our original. My original base of it. 0. Okay. What do I get if I plug in 2? 1 over 11. What do I get if I plug in 3? 3 minus 1 gives us 2 on top. 3 cubed is plus 3 is 30. Okay, we'll leave it like that for now. So yes, or you can reduce it to 1 over 15. But I'm gonna leave it like that. Alright, are we okay with the first 3? Okay, now let's compare that to my second one. What do I get if I plug in 1? What do I get if I plug in 2? 4th, what do I get if I plug in 3? 1 9. We're okay with that. So, again, I want my original function to be smaller. Do we agree that those numbers are smaller? Yeah. Again, if I subtract something from a number, that makes it smaller. If I add it to the bottom, that also makes it smaller. So I'm just making it more smaller by doing both of them. But if it helps to write out the first couple of terms to convince yourself of that, that's fine. But then I could say, since the sum of 1 over n squared, we said it converges because what? 2 is what? Greater than 1, right? Because we used a p-series test on that. Then have time for today.